Hello, everyone, and welcome to the Carbon webinar number 6. My name is Irene Suarez, and I am a researcher at Curtin University in Perth, in Australia. Thank you, everyone, for making the time to join us. I think everyone who has joined us know, but these seminars were started to fulfill the absence of the Carbon conference for the last 2 years, where we normally meet together, share our research, and also network. So that is what we will try to do today with our talk from Professor Joaquín Silvestre-Albero. So we're running this on Zoom. I think everyone is pretty good with Zoom. Just in case, on the bottom of the screen, you have different actions that you could do. Please remain muted during the talk. And at the end of the talk, there will be a chance to ask questions, which you can either post on the chat, or you can just unmute yourselves then when I call your name and you can ask your question. This whole seminar is recorded and it will be uploaded into YouTube. For the questions, you can just raise your hand on the next on that reaction if you want, so then I know that you have a question if you prefer to ask it yourself rather than write. After the talk, Jake will post a link to GatherTown when we will try to imitate the networking that we do during the conference, and I can talk a little bit that afterwards, because now it is my pleasure to introduce Professor Joaquín Silvestre-Albero from University of Alicante. So Joaquín is one of the academic sons of Rodríguez Reynoso. He did his PhD under his supervision in 2003. He then traveled around very prestigious research centers and universities to then come back to Alicante, where he has been researching on green use, using carbon materials for energy storage and gas. And he's one of this year's finalists from the Falling Walls in Berlin, I understand. So congratulations, and we wish you all the luck. So without further ado, I would like to pass it on to you so that you can start your talk.
Okay, thank you very much, Irene, for the nice introduction. So now I share my screen. So here, share. Can you see the screen?
Yes, perfect.
Okay, so first of all, I would like to thank the organizers for giving me the opportunity to show here today part of the work that we have been working in the last maybe 7 years. As you can see here, I belong to the University of Alicante in Spain, and I put here a map so that you can see where we are located. We are in the Mediterranean side. So we are well known because we have really nice beaches there, and our campus is also very nice because it's everything pedestrian, and it's we have really a lot of green areas and everything. So the main topic of my talk, as you can see here, will be to talk about how we did natural storage of natural gas storage in nanoporous carbons, and I will show you how we went from the conventional approach, just designing carbons for physisorption, and how we moved to what is called solidified natural gas storage. No? So before I start with my presentation, let's see if I can go to the next one. Yeah, I would like to just make a small memory about Paco Francisco Rodríguez Reynoso, because he left us last year. And part of the research that I will show you today was initiated in collaboration between him and myself in 2014-15. And I put here a few pictures of him when he was young in Granada, and also in some of the trips when he was with Professor Katsumi Kaneko in Japan, and also in these workshops that Professor Juan Carlos was organizing in Bogota with Matías and Jean Cuquerol. No? So as I told you before, the main idea of my talk today will be to show you how we were moving from the original idea of designing carbon materials, where we are mainly based in the physisorption of the natural gas or the methane molecules, and how after a while we decided to mimic nature, and how we shift to a new approach, or let's say a novel approach that was the combination of natural gas or methane with water molecules in the cavities of carbon materials. So we all know that CO2 emissions, they are growing continuously, and you can see that in the last 40 years or 50 years, the increase has been really significant. No? We have been going from 320 ppm up to 400 ppm. So I checked the value last week, and we are at the moment in 414 ppm. So this is really an important number. This is a huge number, no? And this is just associated with the actual climate change that we are facing in our countries, no? So it's clear that we need to find new fuels, and in this case, hydrogen is a potential alternative. But in the transition from the actual oil consumption to the hydrogen technology, natural gas can be like a very important candidate, because if you see the table here, you can see that compared to oil or coal, the number of the pollutants that you have in the natural gas is quite smaller. No? So you can see that when using natural gas, we have 43% less CO2 emissions to the atmosphere. We are working with a gas, so that means that we have a high efficiency in the combustion. And also, in general, we have a lower concentration of nitrogen oxides, sulfur dioxide, particulates, etc. So let's say that natural gas is like a very convenient bridge to go from the actual consumption of oil to the potential future technology based on hydrogen. Of course, one of the main problems that we have when we are dealing with natural gas is how to store large quantities so that they are significant for, in this case, if we are talking about automotive industry, to make some long distance transportation. No? So the main technology that we are using at the moment for the automotive industry is compressed natural gas. So as you can see here, what we are doing is we are just designing cylinders where we are introducing natural gas at high pressure, so around 20-25 megapascals, and working at 25 degrees. So we are working at atmospheric temperature. Under these conditions, we can reach more or less 250 volumes per volume. And this is a very well-established technology. So there are, in every country, we have cars, buses that they are running with the compressed natural gas. Of course, there are some issues about the safety of these cylinders, but they are, I mean, the technology is quite mature, and at the moment they are certified, and in principle there is no risk when using this type of cylinders, no? At least in majority of countries. Another possibility to transport natural gas is to liquefy it. So we can go down to minus 161, minus 162, and we can make it liquid. And as you can see, we can be working at atmospheric pressure. The main limitation is that you need a very low temperature, and that's why the liquefied natural gas is usually used in these big ships that they are coming from the producer countries. And there you have these big vessels where you can isolate the natural gas at very low temperatures. But of course, this technology is not translated to the automotive industry. We cannot keep these low temperatures in a small car. No? So our main goal was to design a new technology, which is using porous materials as a storage media. No? And the idea was to be able to store a significant amount of methane under milder pressure and temperature conditions. No? And this is what was our main target. No? So as you can see here on the screen, there has been a lot of research in terms of carbon materials, zeolites, metal organic frameworks devoted to the storage of methane. No? And the main goal was to reach, as I say, a significant amount of methane per volume unit at atmospheric temperature and 3.5 megapascals. This is what the Department of Energy is defining. But there is also the possibility to shift to 6.5. So let's say that the main target is to design materials where we can play with these confinement effects. And the goal is to reach 263 volumes per volume, which is rather similar to the compressed natural gas. But as I say, instead of working at 20 or 25 megapascals, to do the same at 3.5 megapascals or maximum 6.5. No? So this is our main objective in the preparation of carbons. Of course, everything that I will show you today is based in methane absorption, but you have to be aware that natural gas is not only methane. You also have hydrocarbons like C2, C4, You also have CO2, nitrogen. So at the end, everything that I will show you is with pure gases. But if you do the same experiments with the real composition, with the natural gas, these additional components, they can have an effect, at least when you are trying to cycle the system, no? In a second cycle or third cycle, because some of these molecules, they can be retained in the porosity of the material. And another thing that I will not show you today is the thermal conductivity issues, no? When we are talking about a cylinder and we are trying to incorporate a carbon material in the inner side of the cylinder, we have to be aware that absorption is exothermic. So if we are thinking about using our car with this adsorbent and go to the gas station and fill the cylinder with natural gas, we have to be aware that at the end there will be a lot of heat in the tank, and sometimes you can even expect an increase in the temperature of even higher than 70 degrees Celsius. And we know that if we increase the temperature in the tank, we are decreasing the capacity of the material. So I will not show you anything about this, but this is also something important. Once you design a material, you have to modify it to improve as much as possible the thermal conductivity so that you can get rid of all these heat processes that they are taking place in the cylinder. All this investigation that we were doing was, as I say, was initiated in 2015. And at this time, there was this nice paper. This is from the group of Professor Hub in Michigan State University. And at this time, they were showing in this paper that materials like, for instance, Moths, they are able to reach these 263 volumes per volume. No? In this case, they were just comparing different Moths. And as you can see here, HCUS1, which is a copper BTC Moth, is able to reach 270. And you see that the working capacity is very good, 190. No? So when we saw this paper, it was like, okay, this is very nice because Moth materials, they can reach the DOE target. But I'm happy with this paper because they were being honest with the readers, because they were saying the following: this is the capacity of the crystal in the powder shape. But as you can see on the screen here, when the student was just filling with Moth sirens and he was applying hand packing, so he was destroying the structure of the material, and he was able to, as you can see, the capacity of the Moth was decreased by 50%. So that was very important. That means that these type of Moths, that they are extremely good for natural gas, at least some of them, they have mechanical instability. And as you can see here, only by pressing the Moth, you are able to break it. So that was a big limitation if you want to prepare, for instance, a monolith. So immediately we were thinking, okay, this is an advantage of carbon. No? Carbon is very rigid. We can apply pressure, and it's very difficult to break the structure. Of course, there are also other advantages, like in the case of the carbon, you have a slip-shaped micropores. So you have a higher packing density compared to cylindrical or spherical pores. The surface of the carbon is rather inert, so that means that you can get rid of the methane, or you can do the desorption quite easily, and that means a high working capacity. We can also play with the physical form. So at the end, you have a large versatility that makes very attractive the design of carbon materials for this specific application. We were taking a look to the literature, and there was this nice paper from Professor Gavins, where he was doing theoretical predictions, and he was doing Grand Canonical Monte Carlo simulations of two different types of pores. No? In one side, they were just evaluating slit-shaped pores, so something similar to what you have in carbon. And they were also just modeling cylindrical pores to mimic what you can have in a zeolite. No? And then they were checking the density of methane in different pore cavities. So in the case of the carbon, what they were observing is that if you are working at low pressures, the higher density is in this type of pores where you can make 2 layers of methane. So we are talking about 0.8 nanometers. However, if we are thinking more about high pressure, as this is the case, you can see that the pores where you can allocate 3 or 4 layers of methane molecules, they have a higher density. No? And in fact, they were estimating how much methane you can store in a pore of, as I say, 3 layers. This is on the table on the right. And as you can see, at 3.4 megapascals, the maximum capacity expected is 249 volumes per volume. So this is more or less like a theoretical maximum that Grand Canonical is predicting for carbon materials. No? you have to increase the pressure to 10 megapascals to reach this 199, which if you do the conversion, this is 270 volumes per volume. So these results, they were anticipating that with carbon materials, it will be very difficult to achieve the DOE target at 3.5 megapascals, but you must be able to do it at 10 megapascals. And there was also something nice. When you compare this performance with the silica or with the zeolite, which is at the bottom, you can see that the absorption capacity of the zeolite, the predictions are much smaller than the ones that you have in the carbon. No? So this is beautiful because that it is showing that if you are able to make a carbon with very narrow cavities, you must get a maximum packing density of the methane molecules, and you must be able to be very close to the DOE target. So that was our main goal. No? We wanted to design carbon materials with a high surface area and with the smaller porosity as possible. No? So at this time, we were very familiar with petroleum residues. So in this case, we decided to use two different residues, vacuum, VR, and decanted oil. And the first thing we were doing an pyrolysis step at 440 Celsius by changing the temperature of the by changing the time of the pyrolysis, so that we could modify the mesophase content of the mesophase pitch. No? So at the end, we were able to obtain residues with a low mesophase content, in this case VR5, that means 5% of mesophase, or changing the time conditions, we were able to go to high mesophase content. No? So we were preparing samples like, for instance, VR93, where you have 93% of mesophase. So basically what we were doing is we were changing the microstructure of the petroleum pitch, as I say, by modifying the pyrolysis time. And as we wanted to prepare narrow cavities, we decided to use KOH because KOH is a very important chemical to develop carbon materials, as I say, with very narrow porosity. No? So we were mixing the petroleum pitch with the KOH in different ratios. We were working either with powder or with monoliths. And you can see here that one important point of the petroleum pitch is that you can make monoliths without binder. No? This is a system with what is called self-sintering ability. And at the end, we had, of course, an activation degree, an activation step at 800 Celsius, and finally the washing to remove the KOH. No? So when we were removing the KOH from the system, and this is a scanning electron microscopy of a lateral section of the monolith, we were able to see micron-sized cavities. No? So we are removing the chemical that we are using for the activation, and of course we leave behind these big cavities, which are very convenient because those will be the motorways for the gas molecules to reach the inner porosity. No? And then the main question was, how is the inner porosity? No? How is the micro and meso cavities in this type of KOH activated carbon? No? So we did nitrogen absorption isotherms, and you can see that the performance is very similar even if you are with a very low mesophase content or with a high mesophase content. No? In general, the isotherms, they look rather similar, and the porosity is also similar. So the main changes are coming from the amount of KOH that you have on the system. If you have a very small amount of activating agents, so 1:1 ratio, you can see that in both cases the isotherm has a very narrow knee. So this is reflecting that you have narrow cavities or narrow pores in your material. No? When we were increasing the amount of KOH to 1, to 2, 2.5, 3, 4, you can see that we are increasing the porosity. We are also widening the micropores, and we are also developing a small amount of mesoporosity. No? And as I say, the performance is rather similar in both cases, independently if you have a low or a high mesophase content. We did an evaluation of the textural properties, and we were able to see that when you are activating the sample with 1,4, you can reach up to 3,500 square meters per gram. No? So this is a very significant surface area for a carbon material. And in these specific carbons where we were working with a high activation degree, we were developing narrow micropores, as you can see here, from CO2 Dubinin, and wide micropores obtained from the Dubinin-Radoskevic equation to the nitrogen data. No? However, for the samples with a very low activation degree, so the 1,1, The surface area is quite good also. We are in more or less 1,500, 1,700. And you can see that nitrogen and CO2 are very coincident. So that means that in these materials, as I was showing before, the porosity is extremely narrow. No? And that's why you have this narrow ring in the nitrogen isotope. Of course, when you see these values, the main idea is, okay, if I want to have a very good methane storage capacity, I need to activate the material as much as possible. No? But you have to be aware that when you activate the material, you are decreasing the density. And if we are talking about design of porous materials for the automotive industry, the density is very important because that will define the volumetric capacity. No? So at the end, it's not very convenient to go to high activation ratios because at the end you will decrease the density and you will have a lower volumetric capacity. So you need to reach a balance. You need activation, but you need to keep also the density of the system. No? So as you can see here, as much as we increase the amount, as much as we increase the amount of KH, what you are doing is you are decreasing the density. No? And this is clearly reflected here in this in the final isotope. No? This is the excess absorption isotopes for methane, gravimetric, and volumetric. No? When you take a look to the gravimetric, as I show you, no? When you have a high amount of KOH, which is the blue one, so you have 1:8 ratio, you have a maximum in the storage capacity. No? We are close to 26 weight%. But when you convert these numbers into volumetric and you take into account the density, you can see that the material with only 1,3 activation, so this is the green one, in volumetric basis can be the winner of all these materials. No? If you take a look to the values that we obtain with this type of carbons that we were developing from petroleum pitch, you can see that our maximum was 200 volumes per volume. So this is lower than the theoretical DOE value. No? Which is, as I told you before, 263. But this is the isotherm that we get from the system. No? So this is the excess absorption isotherm. And we know that the DOE target is referred to the absolute amount absorbed. No? So we have to apply this equation that we have here at the bottom to convert the excess into a storage. No? And when we apply this equation to this DO sample with 1,3 activation, you see that we managed to reach 263 volumes. So that was the DOE target, but at 10 megapascals. So this is more or less in close agreement with the theoretical predictions. Carbon materials, they can reach these values, but we have to go up to 100 bars as a minimum pressure. And just to end up with this part, once we reach these values, we wanted to compare with this special H-cruise Moth that was reported in the literature. No? So in this figure, what we did is we did a comparison of the H-cruise Moth, which is the violet, with our best carbon, which is the blue star. And we decided to take these materials and apply 1 ton of pressure. So we were trying to make like a conforming step. In the case of the violet, which is the Moth, you can see that the Moth can reach 263 volumes per volume at lower pressures than 6 megapascals. No? In the case of the carbon, we need, as I told you before, close to 100 bars. No? But the nice thing is that when we were applying this 1 ton of pressure, the violet diamonds were going down to the brown one. So we were destroying the porosity of the system by 50%. However, in the case of the carbon, we were applying 1 ton of pressure. We were trying to measure again the system, and the absorption capacity was the same. So that means that compared to this specific Moth, in the case of the carbon, you have a higher mechanical stability. And another thing important is that these calculations with Moths, they are done with the theoretical crystallographic density. So this is assuming that we have a perfect crystal. And we know that this is not true. I mean, these measurements were done with a powder, which is really far away from a real crystal. No? So at least the message is that carbon materials, they can compete with Moths. And somehow we have certain advantages in terms of mechanical stability and other properties. No? Once we reached these values, we were wondering how we can improve these numbers, no? How we can get even higher capacities. And at this time, we were thinking, okay, maybe it's more easy to see what nature is doing. No? And we know that in the Earth, natural gas or methane is sometimes associated with water, making what is called hydrates structures. No? So our main focus at this time was, okay, can we make these hydrate crystals artificially, and can we take advantage of the cavities in our carbon materials to promote the growing of these specific crystals? That was our open question, no? Because we knew that in the natural environment, the association of water with methane to make these hydrate crystals, this is a process that needs high pressure and low temperature. And you know that there was always this question about, can we reach high pressures in the cavities of carbon because of the confinement effect? No? So that's why we were trying to see if we were able to do these hydrate crystals in the cavities of carbon. As I told you before, no, these structures, they are made of water molecules, and they are arranged in a specific way so that in the center of the cavity, as you can see here, they can allocate a molecule of methane. And as I say, this is the natural way that you have in Earth to store methane. And this is very interesting because 1 liter of hydrate is able to store 168 liters of methane. So as I say, this is a very interesting way to store large quantities of methane. These hydrates, they are not only restricted to methane, so you can put in the cavities other small molecules like CO2, helium, hydrocarbons, and in fact, depending on the molecule that you're introducing in these cavities, there is a different structure for the system. No? So if you see the table that I put here, the structure number 1, this is the one that you get when you put methane. And this structure is made of small and large cavities. And as you can see, the size of the cavity is 395 angstrom and 433. So this is the perfect size to allocate the small molecules. If you are working with propene or isobutene, you will get the structure number 2, which is a bit more complex. And there is also the structure number 8, the structure H, which is a combination of small, medium, and large cages. And this is only possible when you combine hydrocarbons, like methane with cyclopentene or whatever. In our case, as we were mainly focusing in methane, so we were aware that S1 is the main structure that methane is doing with these water molecules. And as I told you before, there is a range of small molecules that they can fit in the cavities of these gas hydrates. Next question is, okay, where are these hydrates located in the natural environment? Well, if you see the map at the top, in all the continental margins, if you go to the sea and you make a hole, you will find these gas hydrates. Preferentially, methane is the molecule that they are trapping. For instance, you can see here, Australia, you have gas hydrates reservoirs, the same in Japan, India, China, United States. So everywhere at the continental side, you have these crystalline structures that they are trapping methane. The same happens in the permafrost. So if you go to the Siberian region, you can see that the bottom layers of the permafrost, even though they look like ice, at the end, those are crystalline structures where you have water molecules encapsulating methane molecules in the center of the cavity. And they are not only exclusive for Earth. I mean, predictions, they anticipate that Jupiter, for instance, Saturn, Uranus, and Neptune, and even the moons, they have the conditions to allocate methane hydrates. In fact, there was several years ago a mission, which is the Cassini-Huygens, that they were trying to evaluate the oceans that you have in Titan. Titan is the largest satellite in Saturn. And what they observe is that all these lakes that you have in Titan, they are made of liquid. So it's the only moon where you have liquid like on the Earth. But this liquid is not water. This liquid is made of hydrocarbons, so mainly methane, ethane, and also organic solutes. And the predictions, they say that those are the perfect conditions to have methane hydrates at the bottom of these oceans here. So that means that gas hydrates in general are a very general way to store, as I say, methane in the environment, not only in the air, but also in other planets and moons. Concerning the Earth, one of the first studies where they were evaluating these gas hydrates is from 1934, and that was because these gas hydrates crystals, they were blocking the pipelines of the Russians where they were trying to extract natural gas. No? So these blocking effects that you can see here, no? These big blocks which are cylindrical, those are gas hydrates that they are blocking the pipes because there you have these high pressure, low temperature conditions to promote the growing of these crystalline structures. No? Also, in the 60s, they were observing that in Siberia, no? the permafrost was made of these gas hydrate structures. And the point is that the estimated amount of methane, these methane hydrates, is extremely high. It's 74,000 gigatons. So it's much higher than all the fossil fuels that we have been using up to now. So that means that we have a tremendous amount of natural gas on Earth stored in the form of gas hydrates. And this is very attractive for countries, no? Because you can make an exploitation of these natural reservoirs by using this destabilization. No? So, for instance, Japan, I think that was in 2018, they already did some explorations to make tubular holes, to put tubular holes at the sea, to destabilize the system, for instance, by increasing the temperature. And then they were already doing some extractions of methane from these natural hydrates. No? Of course, you have to be really careful because when you are breaking the stability of these seabeds, at the end you produce earthquakes. No? And the same destabilization is also very serious, for instance, in Siberia. You know that this summer there were a lot of fires in the area of Siberia. And if you see the news, in some places there was a collapse of the land. And that was because there was a destabilization of the hydrates. Methane was released to the atmosphere, and that's why the ground was collapsing. No? And this is a very interesting study of 2020. No? By using special devices, they were evaluating the amount of methane that you have in the atmosphere in the peninsula of Timur, in the Siberian region. And you see that this specific summer in 2020, they reached 10 degrees in this area of the Siberian region. No? So that is too much temperature for the stability of these gas hydrates. And as you can see here, when they reached July, so this is the third picture, there were these lines of red color, which corresponds to huge amounts of methane being released to the atmosphere. No? Then they were kept in September. In October, they were, let's say, minimized, the same in November and December. But take a look to what happens in 2021. Temperatures were even higher. And in April already, all the region was completely red. So this is really serious. I mean, there are a lot of methane being released from the Siberian region because of this destabilization of the hydrates due to the climate change. And the point is that all these methane molecules, they are going to the atmosphere and they are also contributing to the climate change. No? So at the end, this is serious because we will get into a circle that it will be really difficult to go out from there. No? So basically what we were trying to do in our research was to take advantage of the confinement effects in the cavities of the carbon and try to promote the nucleation and the growth of these hydrate molecules. No? So if you see the phase diagram of the gas hydrates at 0 degrees, which is the temperature that I will show you in our experiments, around 3 megapascals, so 30 bars is the threshold pressure to go into the hydrate stability zone. So that means that once you pass 3 megapascals, you must start seeing something. No? And our main goal was to do this type of processes, as I say, in the cavities of the carbon materials. When you think about the mechanism and you take a look to the literature, mainly for the bulk phase, what you see is that when people is trying to grow gas hydrates, the first thing you have to do is you have to mix, or you have to put in contact water with a high pressure of methane. There is always an induction time, so you need a few minutes or a few hours until you get some nucleus. And immediately there is the growth of small crystals or small nucleus around this original nucleation size. No? But there is always a problem. In the moment that you make a first layer of gas hydrate at the interface in between the gas and the liquid, the further growing of this gas hydrate is really difficult because you need the methane molecule to diffuse through the crystal to reach the other side. And then what happens is that the formation rate is inversely proportional to the thickness of the hydrate. So at the end, the message is that once you get a layer, the system is stopped. And that makes that the production of bulk gas hydrates is really difficult because it's a very complex system due to the limited gas-liquid interface. So at the end, the people that they are working with artificial gas hydrates in bulk phase, they have slow nucleation and growth kinetics, and they have a low water-to-hydrate yield because, as I say, once you make the first layer, you have a big limitation in the nucleation kinetics. No? That means that if you want to make them in a massive way, you have to modify the system. So either you can incorporate additives that they are promoting the growth of the hydrates. You can also incorporate agitation. So you can do stirring, and then you can improve the contact in between the gas and the liquid. Or the third option is the incorporation of a porous solid. No? And you can see that in the literature, there are already studies with silicas, clays, activated carbon, zeolites, and moths. The main goal is to take advantage, as I showed you before, of the nano-confinement effects and try to grow these crystals under lower or milder pressure conditions. And of course, faster than they are done in the natural environment. No? So here I put an example of a paper from the group of Professor Gabbins. No? And this is nice because in this study, they were doing theoretical calculations of how much is the enhancement of the pressure that you can have in a carbon material. No? And they were predicting that when you have 1 bar in the environment, inside the cavities, you can even stay at 10,000 bar. No? So this is what we were trying to do. No? Why can we take advantage of these confinement effects to promote the growing of crystals that needs high pressure? And that was as I said, that was our main goal in this investigation. There were already papers in the literature dealing with this problem. No? One of the pioneers is from Professor Katsumi in 1998. And at this time, they were working with activated carbon fibers. And they were observing, as you can see here, that the amount of methane absorbed can be improved when you are incorporating water in the system. No? And you see that you have a linear performance. So as much as you increase the amount of water, you can improve the amount of methane. So at this time, they were working, as I say, with activated carbon fibers with a very narrow pore. So I think the size was 1.1. So it's lower than the crystal size of the hydrate. But the group of Professor Katsumi Kaneko, they were predicting that there should be something like a nanohydrate being formed in the cavities. No? And they were predicting something like a concentration of methane in the walls of the carbon. And then the water molecules to be making like a zigzag in between these methane molecules. No? So that was the prediction for these nanohydrates. Also in France, there is a big community of scientific groups working with gas hydrates. And this is a paper from the group of Alain Selzard from 2006. And the same, they were measuring the methane isotherms in the dry material. So you have the type 1 isotherm. And then when they were applying the same isotherms in a system with pre-absorbed water, they had this very strange isotherm. No? So at the beginning, you have like a blocking, and then in a certain point, you have a jump, no? At 4 megapascals. So that was a confirmation that something is happening in the system. No? You reach a point, which is around 3-4 megapascals, where you have a large improvement in the absorption capacity of methane. So there were like the papers that we were using as inspiration for our research. And what we did is we took our carbon materials that I showed you before, and we decided to do similar experiments. So we measured first the dry material, which is the black, and then we were incorporating in the carbon cavities a different amount of water, no? 0.6 gram per gram, 1.1, 1.8, 2.9. No? When we were doing the methane isotherms, at the beginning we were seeing a blocking effect. So water is blocking the cavities, and that's why below, as you can see in the red below, 30 bars, nothing happens. But then in a certain moment, we start also seeing these jumps that I was showing before from the group of Alain. No? And the nice thing is that when we were doing the desorption, there was a very significant hysteresis loop. So something is happening in the cavities of the carbon when we incorporate water and high pressure methane. Even when we were going to this oversaturated sample with 4.1 grams per gram, you see that we have a similar performance. So we have blocking, jump at the beginning, and then we have this progressive increase until we reach 100 bars. No? And the nice thing is that we are able to improve the storage capacity of the system for methane from 22% to 65%. And again, we have this hysteresis that is reflecting that something is happening in the cavities of the carbon. No? Before I told you that in the natural environment, the growth of these gas hydrates takes sometimes even weeks, because once you make the first film or the first layer, everything is very slow. No? And something nice about the carbons is that if we pay attention to the point of 40 bars, so the first that we have the jump, and we go here to the bottom where we have the variation of the pressure in the manifold as a function of time. So this is an indication of how fast we are obtaining this point in the isotherm. You see that in 1 hour, more or less, 1 hour and a half, everything is done. So whatever is happening there, it takes only 1 hour. While, as I say, in the natural environment, you need weeks to make these bulk hydrates. No? As we knew how much methane we are absorbing in the isotherm, and we also knew how much water we had in the system, so we were estimating the ratio of methane to water in the final point of the isotherm. No? And we were doing this for different saturations of the carbon, no? From the undersaturated carbon to the supersaturated, no? Oversaturated. And it's nice because you can see that the stoichiometry is always very similar to the stoichiometry of the methane hydrate in the natural environment. No? You will know that the natural hydrate is 1 molecule of methane, 575 molecules of water. No? And you can see that at least in the samples where we have a significant amount of water, so that means this 2.9 grams per gram and 4.1, you see that the stoichiometry is very similar. So that was anticipating that it looks like we are making gas hydrates in the cavities of the carbon. No? But then we wanted to be sure about this, so we did 2 experiments to confirm the nucleation of the hydrates. One is inelastic neutron scattering and synchrotronic rate diffraction. No? With inelastic neutron scattering, what we observe is that when you have the carbon with methane, all the methane molecules, they start rotating, and at the end, the signal disappears because there is an overlapping in between all the molecules. No? And that's why in the green spectrum, we had the elastic peak at zero millielectron volts. And then there is a very tiny peak at 1 millielectron volts, but extremely narrow. No? So this is because, as I said, the methane molecules, they are rotating, but they are overlapping with each other, and then at the end, you don't get any signal. However, when you have isolated methane molecules, they can rotate freely, and then you have a huge peak. No? And this is what we were observing, for instance, in the red. That was water plus methane at 60 bars. No? And you can see that you have a very beautiful peak at 1 millielectron volts. And this is showing that you have isolated methane molecules rotating. No? So this is a confirmation that methane is trapped in the cavities of these gas hydrates. And the same we observed with the synchrotron radiation. No? We were having at the beginning the pure carbon with water. You see the green. We were going to 0 degrees, so we were observing this ice, hexagonal ice. And then we were pressurizing the system with methane. So when we go from the red to the black, you see that you are shifting from ice to gas hydrate, to methane hydrate. And the nice thing is that you see that the ice disappears. So we have 100% conversion. And this is the most important point about the carbon. We can convert everything, as I say, in 1 hour with complete conversion. Well, I don't know if I have a lot of time left, but just I want to show you also this experiment. This is something that we did with Professor Caroline Kohn. And what we wanted to confirm is that we have 100% conversion of the water to hydrate. No? So we can go directly to the sample with 4.1, which is the one I was showing before. This is the oversaturated sample. And we can go to the warming step. No? So when we do the warming, we have 8 megapascals of methane, and we have 4 grams per gram of water, and we are melting the system. You can see that there is nothing of ice in the calorimetry experiment. No? Everything is just gas hydrate. So this is showing that under these conditions, carbon is able to convert the whole amount of water into gas hydrate. And of course, the same happens if we go to 2.4 grams per gram of water, no? If we are under saturation conditions. So we need to fill the carbons with a lot of water. And this is, for instance, the experiment with 11 grams per gram. And there, of course, we have so much water that then we see the ice melting and the methane hydrate melting. But this is very important because this is showing that with carbon, we can convert all the water to hydrates in only, as I say, 1 hour of experiment. These experiments I will escape. And just to finish, the last experiment that we did in this research was to try to do the in-situ replacement of methane by CO2. No? Because at the beginning, I showed you that these cavities, they can allocate methane or they can also allocate other molecules. So the point is that if we are able to replace the molecules in situ, maybe we can use our natural hydrates to store large quantities of CO2 while taking the methane as a fuel. No? And this is a picture from Professor Katsumi Kaneko that they were explaining that maybe we can use artificial platforms where we can store methane in the form of gas hydrate and in a certain moment replace the methane by CO2. No? The only option to do this experiment was to go to the synchrotron. No? And what we did is, the first thing we wanted to do is to check the stability of the hydrate, because I have to make them. In a certain moment, I have to pump the system and I have to put CO2. No? So the first experiment is to see how stable are these methane hydrates. So we took our carbon, we put a high pressure of methane. As I say, half an hour, everything was converted. We went to minus 120 and then we pumped the chamber. No? And we start warming the system to see how stable is this gas hydrate. And we can reach up to minus 60. And once we reach minus 60, the methane molecules, they are leaving the cavities, and then you go back to ice. No? So you lose the methane, and of course the water molecules, they arrange into an ice structure. Then we were thinking, okay, how flexible is water at these low temperatures to go from ice to methane hydrate and the other way around? No? So in this experiment that I show you here, we were making the methane hydrate at the bottom. We were going to minus 16. So as I show you, we lose the methane and we go back to this red spectra, which is the hexagonal ice. Then we were going to 5 to 2 degrees. We were pressurizing the system with methane. We were going back to the methane hydrate. So this is showing that water is very flexible. If you have high pressure conditions, you make gas hydrate. If you are pumping, you go back to ice. And you can pressurize the system and you can go from ice to gas hydrate and vice versa. And then the final experiment was to do, as I told you before, the in-situ replacement. So what we did is we put methane, we made the hydrates, we evacuate the system, and we fill the chamber with CO2. In this case, 1 megapascal. We started warming the system. In this case, as you have CO2 in the chamber, you can reach higher temperatures and you don't break the gas hydrate. But unfortunately, when we reach minus 6, we lose all the methane. So we went back to ice and we were not able to put CO2 in the cavities. No? So we were like, okay, we were not lucky with this experiment. But of course, we were working with low pressure of CO2 because of the limitations on temperature. No? So what we did in this experiment is once we were in this point of minus 4 degrees, 1 megapascals, we increased the amount of CO2 to 1.5. And then we managed to get this red spectrum, which is the CO2 hydrate. So again, this is showing that that water molecules are very flexible and they can go from ice to methane hydrate or to CO2 hydrate depending on the pressure and temperature condition. No? And this is nice because this is opening the gate, as I say, to replace in situ CO2 by methane, sometimes going through this intermediate ice structure. No? And just to finish, the last slide, I want to show you, just to convince you about carbon, no? Because we are in a carbon community. This is a paper that we published recently about methane hydrate formation in Moths. And those are 2 Moths where we have a huge absorption capacity for water. And I put the comparison with the carbon. No? So you can see that, for instance, this is an AHP Moth, the Moth 5. In the Moth 5, we never managed to go above the red, which is the dry material. So in some Moths, the surface is so hydrophilic that even though you are working at high pressures, you cannot overpass the capacity of the dry system, no? Because the water prefers to be interacting with the walls instead of making gas hydrates. And only with the chromium shock Moth, we managed to increase the capacity of the dry material, but only 33%, while in the case of the carbon, we managed to do it more than 100%. No? So the final message is that for this specific application, so the growing of gas hydrates, carbon is the best system because you combine hydrophobicity, so you are promoting the interaction of the water molecules with the methane, but at the same time, you have a proper wettability of the material. No? So in this sense, we have to say that carbon at the moment is the winner and is the best system. No? So I can escape the conclusions, and just before finishing, I would like to thank Paco because he was the initiator of all these things, Manolo, which is my colleague in Alicante, and Miriam, that was the PhD student that did part of this work. Of course, all the collaborations with ICES, with Outreach, and all the financial support from the European Union and the Spanish government, and of course, all of you for your attention.
Thank you, Joaquin. That was very interesting. So if you're okay now, we will go to some questions. So do we have any questions? You can either write them on the chat, or if you want, you just you can unmute yourself, maybe put your video, so if you are decent, so we can see your face. And yeah, we can ask them. I actually have one question about the destabilization that you were talking about. When you have, is there a way of getting those gas hydrates? Like, is the destabilization problem because they're released too quickly? If we do it slowly, will be less, or how can we solve that problem? Is there any people working on that?
I mean, the point is that when you do the extraction of these natural crystals, no? At the end, you need to break the ice network. No? And the best way to do it is either decreasing the pressure in the surrounding of the gas hydrates or warming them. No? But in any case, you will finish with liquid water. No? And that's why, as the density is different, you will have a collapse of the ground. No? So that's why the in-situ replacement can be a very good option if you are able to keep the hydrates, instead of having methane inside the cavity, replacing it by CO2. Because that means that you will be able to keep the hydrates, and you only are replacing the molecule that is in the middle of the cavities. But at the moment, there were already some issues with the earthquakes, because as I say, no, you are destabilizing the system, and then at the end, all these landfills, they are just collapsing. No? And it's nice what I told you, no? This summer with these fires in Siberia, you can see on the news that they are showing pictures where we have really cylindrical areas where you have a collapse, because there was this, I mean, the inner area, the inner hydrates, they were just being melted, no? And then there was a big amount of methane being released to the atmosphere, no? And they are making this perfect cylindrical structure because of the hydrates.
Jake, is that now?
I do have a question now.
Yep.
Right, thank you so much for such an interesting talk. At the beginning, you mentioned that the pores that were initially, I think, 1.1 nanometers, and you were talking about the structure where you don't actually have enough space for a whole unit cell of the hydrate. I was wondering whether your neutron scattering was able to kind of, or pore size distribution was able to kind of shed some light on the actual structure and how big those, and even what they look like, those hydrates confined in the pores.
I mean, after many years working with this system, we are quite sure that at the beginning, you have the blocking of the porosity because of the water present. Whatever is happening in between 30 and 40 bars is external surface. So you are making hydrates in big cavities or in the external surface of the carbon. And whatever is happening above 40 bars until 100, this is something that is very slow. And in our opinion, this is all mesoporosity and microporosity. No? That's why you need higher pressures to reach these inner cavities and to promote the hydrate formation there. The main problem that we face is that when the referees sometimes they are saying, okay, what is happening in the micropores? No? So we don't have any technique to see how are the crystals in these cavities because we are at the limit of the detection. No? So when I go to the synchrotron and I see this beautiful S1 structure, what I am observing is an average of the big crystals in this carbon. And these big crystals, they are in the big cavities. No? So I don't know exactly what is happening in these small sites. No? That's why the group of Professor Katsumi, they were predicting these nanohydrates. But this is something that we cannot observe. They are too small that we don't have information about the microporosity. But we know that this section of the isotherm is coming from the microporosity.
Thank you.
Any more questions?
I have a couple of questions, if I may.
Sure. Go, Carlos.
A very interesting talk, Joaquín, very nice. I learned quite a bit, actually, but I have a couple of questions. One has to do with the carbon, and the other one has to do with the hydrates that you're talking about. And let me start with the carbon. I understand how you made these monoliths, and I presume in all this work you were talking about the monoliths, carbons, and the potassium hydroxide activation and how you did them. But the volumes that you're talking about, the surface areas were quite large, and the question for this storage applications that you're talking about, it made me wonder about the thickness of the walls. If they were thick enough to withstand the cycling, or has that been looked at? That would be the first question. Has it, how, you talked about the moths being unstable and the carbons being more stable, but how stable would be to repeat the cycling, putting the natural gas in and then out and then back in and back out as you would do in a car? How stable are they going to crumble? Are they going to form powder? Are they going to has that been looked at?
So in this case, for instance, what we were doing in this specific experiment is we were cycling the carbon. So we were able to see that you have a perfect cyclability. And then we were also trying to conform it. So we were applying, as I show you in this figure, we were applying 1 ton to the moth and 1 ton to the carbon. And in the carbon, there was no change in the capacity. So in these specific carbons from petroleum pitch, they have some flexibility, and you can apply pressure, and at the end, you don't change anything in the system. We were reproducing the isotherms, and they were perfectly reproducible.
But they do swell and they shrink as you adsorb and desorb because of the exothermicity, I would presume. But the question would be, how thick would these walls be in these materials, in these pitch-based materials? Do you have any idea, or did you take pictures to see?
No, we never calculate, or no, we never estimate the width of the carbon wall. But I don't know if one question is if you are cycling the system several times, no? If at the end there can be a small degradation of the carbon and you can get powder. No? This is something that we never did. No?
I'd be curious for the practical application. And there's also there are some DFT models and some models that talk about if the walls are thin enough, you can get the interaction from the other side of the walls as to know how it affects the metastability of the faces that you're forming there. So I was just curious. But then the second question is about these structures, and this maybe speaking out of ignorance here, but these hydrate structures that you're forming, they're very fascinating. Yes, you can trap methane, but I was wondering what's so unique about water? Could you do the same thing with alcohol type hydrates or extend this concept to bigger molecules? Is that possible?
Well, we only try CO2 and methane hydrates, but in the literature you have this list of molecules that you can encapsulate in the gas hydrate, no?
Yep.
They are mainly hydrocarbons. I don't know if they have something with alcohols. No, you see, this is the list that they are showing in the literature.
Yeah,
I don't see alcohols there. The point is that you need, for instance, a very good interaction of the hydrocarbon, for instance, with the water, no? And in the case of the alcohol, I'm not sure if you can keep this arrangement of the water molecules while trapping an alcohol in the middle. Maybe the alcohol-water interactions, they can break this 3D order, no?
Well, or maybe some surfactant that had the water or that ability. The question has to do with the water. Yes, you mentioned the hydrophobicity favoring the interaction with water and the methane, but the water itself accessing all the micropores, the deeper confines of the carbon, and these the smallest pores presumably being hydrophobic, not being able to accommodate the oxygen or hydrophilic surfaces. So I was wondering if having some other sort of molecule that would wet or preferentially accommodate differently in the carbon surface would help. So again, I'm speaking out of ignorance. I don't know if that's ever been tried.
We never tried the other. Yeah.
I think what Carlos meant is not substitute the molecule that is trapped, but the water that is surrounded, putting the alcohol instead of the water.
Correct.
Yeah.
Yeah, I was wondering if that's.
I never saw these alcohol hydrates, no? That they are. No, at the end you will have like the alcohol making the cages, no? This is what you mean, and then you will have the methane molecule in the middle, no?
Yeah, methane is a fuel very nice because it packs a lot of hydrogen and that gives you more energy density. But no, there's other things for environmental reasons that we want to trap if possible. So that's what I was wondering.
At the end, what is clear is that the carbon combines, as I say, wettability and hydrophobicity in a proper way to promote this nucleation and growth. No? Because what we are facing, we were working with, as I say, with Moths and with zeolites. So in all this material, it's very easy to have a preferential interaction of the water with the walls. And then when you put the methane, the system doesn't want to make the hydrates. No? And that's why carbon has the perfect chemical surface to promote the interaction of water with methane. No? And this is very important. But as I say, we never try with alcohols or other systems.
Yeah, it just makes me very curious, the chemistry of that. But I learned a lot. Thank you very much. Thank you very much. I enjoy your lecture. Thank you.
Okay, we have last question that we have time for from Alan. Do you want to ask your questions?
Yeah, okay, I think I'm unmuted now. Thank you.
Yes, you are.
Yeah, well, my question kind of follows on from the discussion just before. So if the ability to form hydrates depends on the surface chemistry, you were comparing carbons with Moths. So what if, I wondered if you've done any experiments where you have actually tried to deliberately change the surface of the carbon a little bit, but maybe more oxygenated or less oxygenated, and does that have an effect?
Yeah, in principle, if you have oxygen surface groups, you will modify the interaction of the water molecules with the surface, and then you will change completely the growing of this hydrate. No? We only did some experiments a few years ago, but I'm not really confident. We only did some trials to see the effect of oxygen surface groups, and of course we were observing that you cannot get the same yield, no? Water-to-hydrate yield. Because as I say, when you put oxygen surface groups, you are changing the interaction of the water molecules with the surface. No? So in principle, having oxygen surface groups is not very convenient if you want to make these gas hydrates.
Yeah, okay, thank you. Nice talk, thanks.
Thank you very much, Joaquin. That was an excellent talk. A lot of new things that we have learned. So if you all can join me to thank Joaquin for this excellent talk. The next talk we will have will be on safety concerns and the use of carbon and 2D materials on biodegradable. And that will be by Dr. Alberto Bianco. It will be on the Monday, the 20th of September for the times, depending on where you are in the world. Just check the Australian Carbon Society website to find out what time is where you are. In that website, you can also find the abstract and a bit of about Alberto if you don't know him. I think Jake will put now on the chat a link to GatherTown. If you haven't been before, it's a platform where you create an avatar, just any avatar will do, but just put your real name so that people know who you are, and then you can move around and talk to people just when your two avatars are close to each other. So this is the online way of the coffee breaks. So yeah, thank you very much. And I see you on Monday the 20th.